Today in this tutorial we are going to cover conceptual questions of nuclear physics. Question 1. Why do heavier nuclei have more neutrons than protons? The answer is that heavier nuclei have more neutrons than protons because as the number of protons increases, the electrostatic repulsion between the positively charged protons becomes stronger. This repulsion can cause the nucleus to become unstable and potentially break apart. However, neutrons, being electrically neutral, do not contribute to this repulsion, and can instead help to stabilize the nucleus by providing additional nuclear binding energy. The strong nuclear force, which binds protons and neutrons together in the nucleus, is more effective at shorter ranges. Adding more neutrons to the nucleus can help to increase the strength of the strong nuclear force and increase the stability of the nucleus. This is known as the neutron-proton ratio, which is the number of neutrons relative to the number of protons in the nucleus. Therefore, heavier nuclei require a higher neutron-proton ratio to maintain stability, and as such, they tend to have more neutrons than protons. This ratio can vary between different elements, and there is often a range of stable isotopes with different neutron-proton ratios for a given element. Question 2. Radium has a half-life of about 1600 years. If the universe was formed 5 billion or 5 million years ago, why is there any radium left now? The reason that there is still radium present in the universe despite its relatively short half-life of 1600 years is due to the large amounts of time that have passed since the formation of the universe. For example, if the universe was formed 5 billion years ago, this means that there have been roughly 3.1 times 10 to the 18 seconds since its formation. Given radium's half-life of 1,600 years, this means that there have been approximately 1.9 times 10 to the 15 half-lives of radium during this time. The amount of radium that remains after each half-life is reduced by half, so after 1.9 times 10 to the 15 half-lives, only a very small fraction of the original amount of radium would remain. However, due to the immense size of the universe and the vast amounts of time that have passed, even small amounts of radium can still be present. It's also worth noting that radium is not formed directly from the Big Bang or other cosmic events, but rather through the decay of heavier radioactive elements such as uranium and thorium. These elements have longer half-lives, allowing them to persist over billions of years, and they continually produce new radium through their decay processes. Question 3. If we focus our attention on a specific nucleus in a radioactive sample, can we know exactly how long the nucleus will live before it decays? No, we cannot know because the decay of a nucleus is a probabilistic process, meaning that it is impossible to predict the exact moment when a particular nucleus will decay. However, we can predict the probability that a given nucleus will decay within a certain time interval. The probability of decay is characterized by the half-life of the nucleus, which is the amount of time it takes for half of the nuclei in a sample to decay. For example, if a sample has a half-life of 1 hour, then after 1 hour, half of the nuclei will have decayed, and after 2 hours, 3/4 of the nuclei will have decayed. The decay of a nucleus is governed by the laws of quantum mechanics, and the timing of each decay event is fundamentally random. However, by observing a large number of identical nuclei, we can make statistical predictions about the behavior of the sample as a whole. Question 4. Why are neutrons such good projectiles for producing nuclear reactions? Neutrons are often used as projectiles for producing nuclear reactions for several reasons. 1. Lack of charge. Neutrons have no electric charge, and therefore do not experience the repulsive electrostatic forces that can hinder the penetration of positively charged particles, such as protons, into the nucleus. This makes neutrons highly effective for inducing nuclear reactions, as they can easily penetrate the nucleus and interact with the protons and neutrons within it. 2. Similar mass to protons. Neutrons have a mass that is very similar to that of protons, which means that they can effectively transfer kinetic energy to a target nucleus in a collision. This makes them highly effective at inducing nuclear reactions, as they can transfer energy to the target nucleus and cause it to become excited or even break apart. 3. Ability to produce new isotopes. When a neutron collides with a target nucleus, it can be absorbed by the nucleus, which can then become unstable and decay through beta emission or other decay modes. This can produce new isotopes that may be of scientific or practical interest, such as isotopes used in medicine or industry. 4. Neutrons can induce fission. When a neutron is absorbed by a heavy nucleus such as uranium-235, it can cause the nucleus to become unstable and split apart through fission. This releases a large amount of energy and additional neutrons, which can in turn induce further fission reactions, leading to a chain reaction. This is the basis of nuclear power and nuclear weapons. Question 5. Why neutrons activated nuclides tends to decay by B- rather than B+. When a neutron is absorbed by a nucleus, the resulting nuclide is often left in an excited state. This excited nuclide may then decay through several different decay modes, including beta-, beta, decay, and beta+, decay. In beta- decay, a neutron in the nucleus is converted into a proton, and an electron and an antineutrino are emitted from the nucleus. This results in an increase in the number of protons in the nucleus and a decrease in the number of neutrons. This type of decay is often preferred for activated nuclides that have an excess of neutrons, as it helps to restore the balance between protons and neutrons in the nucleus. In contrast, beta+ decay involves the conversion of a proton in the nucleus into a neutron, with the emission of a positron and a neutrino. This type of decay is preferred for nuclides that have an excess of protons. However, in activated nuclides that have an excess of neutrons, the probability of beta+ decay is generally lower than that of beta- decay, due to the lower binding energy of the resulting nucleus. The probability of a nuclide decaying by beta- or beta+ decay depends on several factors, including the mass of the nucleus, the number of protons and neutrons in the nucleus, and the energy of the decay products. In general, the probability of beta- decay is higher for nuclides with an excess of neutrons, while the probability of beta+ decay is higher for nuclides with an excess of protons. Question 6. Why are small and large nuclei unstable? Small and large nuclei can both be unstable for different reasons. Small nuclei, those with fewer than 20 protons, tend to be unstable because they have a high surface-to-volume ratio. This means that a large fraction of the nucleons, protons and neutrons, are on the surface of the nucleus, where they experience weaker binding forces than nucleons in the interior. As a result, small nuclei tend to be less tightly bound and more prone to disintegration through processes such as alpha decay, which involves the emission of a helium nucleus, 2 protons and 2 neutrons, from the nucleus. Large nuclei, those with more than 83 protons, tend to be unstable because they have too many protons to be held together by the strong nuclear force alone. The electrostatic repulsion between the positively charged protons becomes stronger than the strong nuclear force, making the nucleus less stable. Large nuclei can decay through a variety of processes, including alpha decay, beta decay, and spontaneous fission, in which the nucleus splits into 2 or more smaller nuclei. However, not all small and large nuclei are unstable. There are many stable nuclei in both size ranges, and the stability of a nucleus depends on the specific configuration of protons and neutrons within it. Question 7. Why is conventional fission nuclear reactor not able to explode as a bomb? A conventional fission nuclear reactor is not able to explode as a bomb because it does not contain the necessary conditions for a rapid and uncontrolled chain reaction to occur. In a nuclear reactor, the nuclear chain reaction is controlled through the use of control rods, which are made of materials that absorb neutrons and slow down or stop the chain reaction. These control rods can be moved in and out of the reactor core to adjust the rate of the chain reaction and maintain a steady power output. In contrast, a nuclear bomb relies on an uncontrolled chain reaction in which the rate of neutron production and absorption is not regulated. The chain reaction is triggered by bringing together enough fissile material, such as highly enriched uranium or plutonium, in a configuration that allows for a critical mass to be achieved. This critical mass is the minimum amount of fissile material needed for a self-sustaining chain reaction to occur. To achieve a nuclear explosion, the fissile material must be compressed and heated to extremely high temperatures and pressures in a very short period of time. In a nuclear reactor, the conditions needed for a nuclear explosion to occur are not present. The fuel is not enriched enough to sustain an uncontrolled chain reaction, and the reactor is designed to operate at a steady power output, rather than the rapid energy release associated with a nuclear explosion. The control rods and other safety systems are also designed to prevent an uncontrolled chain reaction from occurring and to shut down the reactor in the event of an emergency.